Okay, let's unpack this. Think about the tools you rely on every single day,
Mm.
the software that forms the bedrock of your work.
Mm.
What happens when those fundamental pieces aren't perfectly consistent?
Right.
Even, subtle differences in how they interpret information can lead to these really frustrating bugs that are just incredibly difficult to pinpoint.
Yeah, it's like having two essential manuals that seem identical pretty much at first glance, but in some like rare situations they give conflicting instructions.
Hmm.
And if your whole process relies on both manuals, well, you're kind of guaranteed to hit these unpredictable errors eventually.
Exactly. And that underlying tension is, well, that's what we're diving into today. We're exploring how some seriously powerful computer science theory, the kind of involving things called automata, and how we can teach computers to learn them, can be used to systematically hunt down these sorts of compatibility nightmares.
Yeah, and something as core as the software that actually parses your code.
Right, the parser itself.
Our source for this deep dive is a fantastic talk from Ruby Kaigi by Hiroya Fujinami, known online as Make Now Just. He really showed how he took these advanced research concepts and applied them directly.
And found a real bug.
Yeah, found a real impactful bug right there in the Ruby programming language itself.
Wow. Okay, so our mission here is to understand the headache caused by having multiple implementations of something critical, like a parser.
Uh-huh.
See how viewing them through the lens of automaton theory offers this, elegant solution.
Right.
Figure out how machine learning algorithms turn that theory into a practical bug-finding tool.
Making it actually usable.
Exactly. And finally, see how this specific approach actually uncovered a real issue in Ruby.
And the specific context here is Ruby, which, as you probably know, currently uses two main parser implementations. There's the older, long-standing parsed,
The classic one.
and the newer, increasingly important Prism.
Right. And the absolutely crucial challenge for anyone developing or running Ruby code is ensuring that these two parsers behave identically. You just need your program to work the same way every single time, regardless of which parser is running under the hood.
Let's dig into that problem a bit more. As you mentioned, Ruby currently navigates the world with two primary parser implementations.
You've got the original heavyweight, parsed.y. This one's been the standard for ages, built with a classic tool called Bison.
Mhm.
For a long time, it was this single monumental file. I think the talk mentioned something like 16,000 lines of parser definition at one point.
Yeah, huge. And then there's Prism. This is a more modern take, written in C, designed with a focus on better memory usage and, crucially, built to be easily embedded.
So other tools can use it.
Exactly. Used as a library by other tools in the Ruby ecosystem, like code formatters, linters, or even different Ruby implementations like JRuby or Truffle Ruby.
Okay. And while the core Ruby language itself uses these two, you're right, the broader world of Ruby gems and libraries adds complexity. Some might wrap these parsers, others might have their own, limited parsing logic. The potential for subtle differences just multiplies.
So, from a developer's point of view, this is where the pain comes in. Having multiple parsers isn't really a feature if they disagree.
No, definitely not.
If your code parses fine with parsed.y, but throws an error, or worse, produces a different result with Prism, you're facing a compatibility bug. That's the central challenge Mr. Fujinami was tackling.
And he talked about the standard ways people usually try to find these. You write a massive number of unit tests trying to cover every syntax variation you can think of.
Right. Or you take a kind of brute force approach. Parse huge amounts of existing real-world Ruby code, like digging through all the public gems with both parsers and compare the outputs, just looking for any mismatch.
And there's also fuzzing, which sounds chaotic, but it's actually quite strategic. You generate these semi-random code sequences and feed them to both parsers, hoping to stumble upon something where they diverge, right? Either error handling or valid syntax.
Yeah, exactly. But while these methods are absolutely essential, they find tons of bugs.
Sure.
The talk highlighted their limitation. They rely heavily on volume. You're either testing specific examples you thought of, or you're just hoping randomness or existing code hits the right spot.
Mm-hmm.
And this makes it really easy for subtle, rarely used, or maybe even new syntax combinations to just slip through the net. Bugs can hide there.
Okay, so volume and luck aren't enough. Not for full confidence, anyway. This is where the more rigorous approach comes in. Could theoretical computer science, specifically automaton theory, offer a more systematic way to guarantee compatibility?
That's the core idea. And to understand how, we need a brief, pretty accessible dive into automaton theory itself. Now, that might sound abstract, but the fundamental concepts are actually quite intuitive.
Okay, let's try it. What exactly is an automaton in this context? Layman's terms.
Okay, so at its heart, it's a simple mathematical model of a machine that processes sequences of symbols. Think of it having a set of internal states it can be in.
Like different modes.
Kind of, yeah. It has a starting state and rules called transitions for how it moves from one state to another based on the input symbol it reads. And crucially, some states are marked as accepting states.
So it reads a sequence, maybe letters or symbols from some defined alphabet, right?
Yep.
It transitions through states based on those symbols and ultimately decides whether to accept or reject the whole sequence based on where it ends up, the final state.
Precisely. If it ends in an accepting state, the sequence is accepted, otherwise rejected. And here's where it gets really interesting for software. Finite automata have this deep, fundamental connection to regular expressions.
Ah, rejects. Okay.
Yeah. Anything you can describe with a regular expression like, valid email patterns or simple text structures can be recognized by a finite automaton and vice versa. They represent the same class of languages, sets of sequences,
Yeah.
but automata are far more powerful for manipulating and combining these sets of sequences they recognize.
Combining sets. You mean like set operations on the language is the collection of all sequences that an automaton accepts.
Exactly. The standard set operations apply. Union, which is sequences accepted by either automaton.
Okay.
Intersection, accepted by both. Difference, accepted by the first but not the second. But the one that's really crucial for finding incompatibility is the symmetric difference, sometimes called XOR.
Symmetric difference, right? That's things in one set or the other, but not in both.
You got it.
So sequences that are accepted by one automaton, but not the other.
Exactly. It's the set of sequences that are in one language but not the other. And the real power of automata here is that you can actually calculate the automaton that represents this symmetric difference between any two original automata. It's a constructive process.
How does that calculation work? Conceptually, I mean.
Well, imagine you have two automata, let's call them A and B. To build the automaton for their symmetric difference, you create a new automaton whose states basically represent pairs of states, one from A and one from B.
Okay, tracking both simultaneously.
Exactly. When you feed this new automaton an input symbol, it makes A transition according to its rules and B transition according to its rules simultaneously. The crucial part is the new symmetric difference automaton reaches an accepting state only if the corresponding paired states in A and B mean one is accepting the sequence so far and the other is rejecting it. So the end result, the final state of this combined machine, accepts a full input string if and only if A accepts it and B rejects it, or RB accepts it and A rejects it.
Okay, I see the link to our parser problem now. That's clever.
Yeah.
So if we can somehow represent our different parsers, parsed.y and Prism, as automata, then calculating the symmetric difference between their automata will give us a new automaton that accepts only the code sequences where the two parsers behave differently.
That's the core hypothesis, precisely. A parser can be modeled as an automaton.
And specifically, this parser automaton accepts a sequence of input text if and only if that particular parser, say Prism, can successfully parse that sequence of code without reporting a syntax error.
Right. It basically defines the precise set of input strings that parser considers valid Ruby syntax.
So the theoretical roadmap is clear. Get the automaton for parsed.y, get the automaton for Prism, and calculate their symmetric difference. Boom.
And the outcome tells you everything about their compatibility, well, within the scope of what the automata represent. If the resulting symmetric difference automaton is empty, meaning it accepts absolutely no sequences then?
They're compatible, at least as far as this model goes.
Exactly. As far as these models are concerned, the parsers are compatible. No inputs exist where one accepts and the other rejects.
But if that symmetric difference, Automaton does accept sequences.
Then those sequences are your compatibility bugs. They are the specific pieces of code that successfully parse in one system but fail in the other. And automaton theory offers ways to not just know they exist, but potentially even help you find examples of those exact problematic strings.
Okay, the theory is elegant. I get it. Represent parsers as these math machines, use math operations to find the differences. But here's the massive practical hurdle, right? Just say download the automaton definition for parse.a or Prism. They weren't built that way. How on earth do you get the automaton for a complex existing piece of software?
Right, that's the million-dollar question. And this is where the second crucial piece comes in, automata learning. This is a whole field of algorithms dedicated to inferring the mathematical model, the automaton, from a system by treating that system essentially as a black box.
You mean like you interact with the parser, you watch what it does, and the algorithm kind of reverse engineers the machine inside.
Precisely. The talk specifically highlighted a type called active automa learning, focusing on the well-known Angloan L-star algorithm.
Active learning. How's that different from just, say, feeding it a pile of data?
Fundamentally different, yeah. Passive learning just observes inputs and outputs from pre-existing data. Active learning interacts with the system directly. The algorithm isn't just watching, it's actively asking questions of the system it's trying to learn. It needs a teacher or an oracle.
Ah, okay, this is where the Akinator analogy comes in from the talk. The algorithm is like the lamp demon asking questions.
Yeah, exactly.
And the system, in our case, the parser, is
Yeah.
providing the answers. Like, does it parse? Yes, no.
That's a great way to think about it. The L-star algorithm primarily uses two types of questions or queries to the system, which acts as this teacher. First, membership queries. This is the simpler one. The algorithm asks basically, hey system, does this specific string of input symbols parse successfully for you?
Okay.
The system, the parser, gives a straightforward yes or no answer. The algorithm uses these answers, lots of them, to build up its understanding of the system's behavior, which inputs are accepted and which aren't.
Okay, so it's gathering facts about what inputs are valid. What's the second type of question?
The equivalence query. This one's more complex and more powerful. Once the algorithm feels kind of confident it understands the system based on all the membership queries it's done.
It has a hypothesis.
Exactly. It proposes a candidate automaton it has learned so far. And it asks the system, does this automaton I've built perfectly match your behavior for every possible input string? Now, if the proposed automaton is correct, the system confirms equivalence, and the learning is done.
But if it's not correct,
If it's not correct, the system must provide a counterexample, a specific input string, where the learned automaton and the real system behave differently. One accepts, the other rejects.
so the counterexample is like the gold standard feedback. It shows the algorithm exactly where its current guess went wrong.
Absolutely. That counterexample is crucial. The algorithm takes that counterexample, uses it to perform more targeted membership queries to figure out why it was wrong, refines its proposed automaton, and then issues another equivalence query.
It just keeps cycling.
Yep, this cycle repeats. Gather info with membership queries, propose an automaton, test with an equivalence query. If wrong, use the counterexample to learn more, refine, and repeat until the system finally confirms the learned automaton is equivalent to its actual behavior.
Okay, the chain of thought makes sense now. You use automaton learning, like L-star, to get the theoretical automaton for parsed.y in Prism by querying the actual parsers. Then you calculate the symmetric difference of those learned automata to find code sequences where they disagree.
That's the practical application of the theory. However, and this is a big however, the talk was very clear about a significant hurdle right now. Basic L-star is designed to learn regular languages.
Which we said Ruby isn't.
Exactly. Ruby's grammar is much more complex. It's at least context-free, possibly more, requiring models like push-down automata to handle things like nested structures properly, parentheses, brackets, begin blocks. So you simply cannot learn the full, complex Ruby grammar with standard L-star.
Okay, so the basic tool isn't powerful enough for the entire language definition. That's a major limitation.
It is for the whole thing. But extensions to L-star do exist for learning more complex language classes. The talk specifically mentioned visibly push-down automata, or VPA, as an example.
Okay, VPA.
Yeah, these are a specific type of push-down automaton which handle nesting using a stack, but they're designed for structures where the nesting is kind of visible in the input stream. Think matched parentheses or brackets, where the opening symbol tells you something is starting and the closing symbol tells you it's ending.
Makes sense.
So while VPA still isn't capable of learning the entire complexity of Ruby, it's better suited for handling nesting than simple finite automata, and it was chosen for this project as a pragmatic step, especially targeting bugs related to those kinds of bracket or parenthesis structures.
And the speaker actually built a library for this. That's pretty cool. He created Lernen, which is a library for automaton learning written in Ruby.
Yes, he highlighted it as being designed to be accessible, which is great. It implements algorithms like L-star and variants, including VPA learning, and apparently can even help visualize the automata it learns.
Visualizing the state machine, that could be useful.
Definitely. He showed how you use lernen.learn. You give it the alphabet of input symbols you care about, and then a block of Ruby code that acts as the system or teacher. Essentially, that block calls the parser you want to learn, like prism.parse, and just returns true or false based on whether it succeeded or raised a syntax error.
Got it.
Now, the key strategy used for the Ruby parser experiment, given the challenge of learning the full grammar, was to drastically limit the scope. Instead of trying to use the entire set of Ruby tokens as the alphabet, which would be huge and complex, they focused on a very small subset relevant to a bug they suspected or perhaps had already found manually. It was just open bracket, colon, literal identifiers like O, and close bracket.
Just those 4 types of tokens.
Yeah. This severely restricted alphabet allowed them to use VPA learning within Lernen to learn the behavior of parsed, specifically for sequences composed of just these tokens, paying close attention to the nesting rules of ang-aim.
So they learned a small, simplified automaton representing parse Beatty's behavior just for these bracket colon sequences, and another tiny automaton for Prism's behavior with the same limited sequences.
Precisely. Little specialized automata.
Yeah.
And then they used Lernen's fine separating word method.
Yeah.
This method basically takes 2 learned automata, calculates their symmetric difference internally, and then searches for an actual input string made of just in this case, that is attempted by one automaton but not the other.
And that string is your potential bug-revealing counterexample.
Exactly.
Okay, moment of truth. Did it actually find anything? Did the theory and the learning algorithm expose a real bug using this limited approach?
Yes, it absolutely did. The process successfully identified the exact sequence, open bracket, literal, colon, close bracket like a scald bread, that constituted the specific bug Mr. Fujinami had previously found manually.
That is fantastic. Seriously, it validates the entire approach. It shows that it works not just in theory on toy examples, but against real complex software, even with limitations.
It's a really powerful demonstration. Combining this rigorous theory with automated learning can find real, previously unknown compatibility bugs in practical systems. And importantly, the bug found was reported to the Prism project and subsequently fixed.
That's a concrete victory. Abstract computer science making a tangible difference in the real world of software development. Very cool.
It truly is. And the talk wasn't limited to just parsers either. It suggested this approach has broader applications based on this success.
Right, because the core idea isn't parser specific. What's the general principle for where else this could be used?
Well, the general use case is pretty much anytime you have 2 different implementations of what is supposed to be the same system, and you need a rigorous way to verify that they actually behave identically for all possible inputs.
Oh, I see. Like maybe when you rewrite or refactor a major piece of software?
Exactly. That was a specific example given. Comparing an older program with a heavily refactored version, or even a complete rewrite, perhaps in a different language or using a different style, you want to be sure the new version didn't accidentally introduce subtle functional differences.
Yeah, those are notoriously hard to catch with just testing.
Right. Automaton learning could potentially uncover those unintended behavioral changes that slip through traditional QA.
Yeah, that's incredibly powerful for software quality assurance. It's not just relying on tests you thought of. It's potentially a more systematic check for functional equivalence. Now, looking forward, the ultimate dream, I guess, would be learning a perfect automaton for a full parser and mathematically guaranteeing complete compatibility between parsed.y and Prism. Right.
That's the big picture goal, absolutely. But the source was very realistic about the significant challenges that still make that a very hard research problem today.
Okay, what are the main obstacles stopping us from doing that right now?
Well, first, just scale. Real-world programming language parsers are, from an automaton perspective, massive. Their equivalent automata would likely have thousands, maybe tens of thousands of states, maybe more. And they process a large alphabet of different tokens. The computation required for current L*-style learning algorithms tends to grow exponentially with the number of states and the alphabet size. So learning the full precise automaton for a real parser is just computationally infeasible with today's techniques. It would take forever.
Right. Exponential growth is definitely the classic spoiler for scalability in computer science.
Indeed. Second, grammar complexity. As we touched on, even the extensions like VPA aren't sufficient to learn the full complexity of a language like Ruby. The talk used the example of just the simple string foo and how complex the parser's logic is to figure out if that foo is a local variable, part of a method call, a symbol, etc., depending on the surrounding context.
Yeah, context sensitivity is tough.
Very. New, more powerful learning algorithms are needed that can handle these richer, context-sensitive grammar structures effectively.
So we need better math, better algorithms just to capture the nuances of the language itself before we even worry about scale.
Pretty much. And thirdly, there's the challenge of learning beyond parse success. The method demonstrated learns whether a string parses successfully or not. Yes, no. But ideally, for true compatibility, you want to know if the resulting syntax tree, the structured representation of the code's meaning, is identical between the two parsers.
Ah, right. You don't just want them to agree it's valid code. You want them to agree on what it means, the whole structure.
Exactly. Learning an automaton that somehow captures the structure of the output, the AST, alongside whether parsing succeeded is a significantly harder learning problem than just learning the set of accepted strings.
Okay, so that's a whole other level of complexity.
That makes sense.
So it's definitely still cutting-edge research, this area, but one with clear, exciting potential, even with these big challenges.
Absolutely. It's really pushing the boundaries of how we can apply formal methods in machine learning to verify and understand complex software behavior in new ways.
So as we wrap up this deep dive then, we've really seen how bringing together the theoretical elegance of automata with the practical power of machine learning algorithms gives us this systematic and frankly effective way to tackle compatibility issues, even in really complex software like programming language parsers.
Yeah, and crucially, it's not just theory. It was proven by finding that real bug in Ruby, which led to an actual fix. That's the payoff.
Definitely. And the core idea, as you said, extends far beyond just parsers. This fundamental concept of using automaton learning to rigorously compare the behavior of different implementations.
Yeah.
It has immense potential wherever ensuring two systems act the same is critical. Refactoring, rewrites, maybe even protocol implementations.
Could be, yeah. Anywhere equivalence matters.
And for anyone listening who's curious to maybe explore this hands-on, the Lernen library that Mr. Fujinami built is out there, available as a tool in Ruby.
It certainly makes the practical application of these somewhat abstract concepts much more accessible than trying to build everything from scratch.
Yeah, for sure. So given the hurdles we talked about, scale, grammar complexity, but also the clear success demonstrated by finding that real bug, it really makes you wonder, what other complex systems that we currently treat as opaque black boxes could be cracked open and rigorously tested using this kind of learnable automaton approach?
Yeah.
Could this type of behavioral verification eventually become, a standard step in developing critical software down the line?
That's the provocative thought, isn't it? It's a fascinating direction for ensuring software correctness and reliability in the future.